Welcome, business statistics students. This is our first edition of the work from home coronavirus version of business statistics. You know what I would love for these videos to be perfect and be crisp, for me to edit out all of my stutters and uhs and mistakes and times when I write sloppy. Unfortunately, that's not going to happen because we have to make multiple of these videos for every class every week. And just in order to make it through, I'm going to have to just do it just like I do in class. And that is, I'm going to say things that are confusing sometimes. I'm going to stutter sometimes. I'm going to make mistakes sometimes. And I apologize right now. And what I would suggest that you do is just get frustrated with me and yell and scream and let your family think you're crazy. They may already think you're crazy. And then just go on with your day. What you can see is I have a whiteboard. We're going to be writing on the whiteboards, and we're going to be talking about them as we go through these times. Right now we're in chapter 5. Chapter 5 is an important chapter for us. Chapter 5 kind of shapes the way we're going to think about statistics from here on out. We're not going to have a lot of problems from chapter 5, but instead we're going to have a way of thinking that's going to inform what we do throughout the rest of the semester. So chapter 5 has two really big ideas. It has the idea of sampling distributions, and it has the idea of the central limit theorem. And in this video, we're going to talk about both of these ideas and hopefully make some sense of them as we go forward. Okay. At the heart of this chapter, though, is the question of what happens when you roll a dice. So what happens when you, I guess I did flips. Maybe I was going to do a dice roll. So what happens when we roll a dice once versus roll a dice, say 10 times. And this is one of these in-class activities that I really enjoy, and I was going to make you all do it. So if you'd like to grab a dice, you can. It's not going to be near as helpful or meaningful at home. But what I was going to do is I was going to have you each roll a dice and tell me what you get. So for example, there's a 1, and then I was going to put the results on here. And so there's a 1. Hey, there's a 1. Maybe I'll roll 1 every time. Oh, no, I rolled a 3. And what would we expect to happen if we rolled a dice over and over and over again? Well, what we'd expect to happen is I would expect some of you to get kind of every number, and I would expect every number to show up kind of roughly the same. Some, because of just the way luck happens and the way probability happens, some numbers might have a little bit more and some numbers have a little bit fewer. But overall, you'd expect all the numbers to show up and all the numbers to show up kind of with close to the same amount. Well, I'm going to compare these type of results to what happens if I roll the dice 10 times. And let's just do it once, just for the sake of us, and then see what happens. So I'm going to roll my dice 10 times. And so we get the number 4, 6, 6, 2, that was a 1, 1, 1. This dice likes a 1, doesn't it? 3, 2, let's see, we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, and 5 is the last one. So now my goal is to average all of these out, and so let's see if I can do that really quickly. These make a 10, these make a 10, and then I've got 6, 7, 8, 9, 10, these make a 10, and then there's one extra. So it looks like I have 31 divided by 10. So 3.1 was my average. And so what I would have done in class is I'd have had every single person roll the dice 10 times and every single person come up with their average. And then what we'd do is we'd put those averages here on our chart. And what you notice is my average was right here. And if you think about it, when we rolled the dice once, we had lots of different options. It was not unusual for someone to get a 1 or for someone to get a 6. When we rolled the dice 10 times, it would be extremely unusual for someone to get a 1. Or someone to get a 6. Because what would a 1 mean? A 1 would mean that you rolled 1 every single time for all 10 rolls. And even something like a 1.5 would be extremely unusual, because that means you rolled it 10 times and you got a total of 15s. That means you mostly got 1s and 2s. You probably didn't get any big numbers like 6s and things like that. So even a number like 1.5 would be unusual. So what would we find if we did this for a whole class? If you did this for the whole class, you would get that most of us are kind of piled here in the middle. Most of our results are kind of right here, right around the between 3 and 4 range. And so what we see is that the center point stays about the same. So if you look up here, if I were to take the center of all my 1 rolls, it's right here at about 3.5. If I take the center of 10 rolls, it's about 3.5. But what's the difference? The difference is 1 roll, it's not unusual for things to be spread out quite a bit. In 10 rolls, most of the numbers end up being clumped right around the center because you rolled it 10 times and averaged it. Okay, so that is, in many ways, the heart of what we really want to talk about today. And so this is what we call a sampling distribution. And so a sampling distribution is the distribution of x bar across all possible samples of size n. And so what we want to think about is the difference between the distribution of the results. So distribution for 1 roll. And if I thought about that problem we just had, my distribution for my 1 roll might look something like this, where I have 1, 2, 3, 4, 5, oh, I didn't put enough, 6. So my distribution for 1 roll might look something like this, where each possible outcome had the same likelihood. So each number has the same result. But the sampling distribution my sampling distribution for 10 rolls is going to look something like this, where 3.5 is in the middle, and most of my numbers are right there close to 3.5, and the numbers on the outside aren't really possible anymore. And so this is the idea of a sampling distribution. The big idea is moving from thinking about 1 roll of the dice to thinking about 10 rolls of the dice. But we're not just rolling the dice 10 times. I'm rolling the dice 10 times. You're rolling the dice 10 times. Your classmates are each rolling the dice 10 times. And we're taking all of those possible rolls. So we each roll the dice 10 times, and we're saying, what are all of the outcomes look like? What's my collection of every possible collection of 10 rolls look like? And the answer is most of the 10 rolls have averages close to the middle, but some of them are a little spread out, versus if we all roll the dice once, we could get all sorts of different results. So what I really want to ask is this question, and that is, what happens to the size of the sample as what happens as the size of the sample gets larger? This is a good spot for you to just pause for just a second, and I want to particularly think about what happens as the size gets samples. What happens to the average, and then what happens to the standard deviation? So we have these two distributions. We had our distribution for 1 roll, or distribution for 10 rolls. What if we were to make it 100 rolls, or 1,000 rolls, or 1,000,000 rolls? What would happen to the average? What would happen to the standard deviation? So this is a good time for you to pause, and I'm going to do this kind of throughout the problems. I'll just draw a little pause button for us here, and that just means take a moment, try the problem, think about the problem for a second, and try to answer the question, and then come back and we'll answer it together. So pause, ask yourself, what's going to happen to the average, what's going to happen to the standard deviation, and then we'll talk about it. So pause. All right, hopefully you actually did that. If you didn't, then that was probably a little bit of an awkward interlude. At any rate, what happens as the size of the sample gets larger? Well, I have a picture of some things for us, and this is from your notes, so I'm just going to show us what happens in the notes. And so this was the example where we had our funny dice that had 1 1, 2 2s, and 3 3s. So here's what happened when you rolled it once. Here's the distribution if you roll it twice. Here's the distribution if you roll it 4 times. Here's the distribution if you roll it 8 times. And it can keep going on and on and on. Okay, and as I look at this, what do I notice about the average? Each time, my average is always 2.3. And that kind of makes sense, because if we thought about this example, the center of your values was somewhere right around here, versus the center is kind of right, the center stays the same place, doesn't it? If you're averaging dice, if you roll 100 dice, you'd expect to average 3.5. If you roll 1,000,000 dice, you also expect to average 3.5. So what happens to the average? The average stays the same. Okay, but what happens to the standard deviation? Well, what you notice is that the standard deviation on each of these, they become less and less spread out, and they become closer and closer to this value. So look at our standard deviations, we get 0.7, 0.5, 0.3, 0.2. The standard deviation is getting smaller and smaller. And if you remember, what does standard deviation mean? Standard deviation just means how spread out are our numbers, how spread out is the distribution. Over here, notice 1s and 6s are not unusual. It's not a surprise to get any number from 1 to 6. If you roll it 10 times, all of a sudden it becomes really surprising to get 1 and 6. If you were to roll it 100 times, then your average would be even closer to 3.5. If you roll it 1,000,000 times, your average should be really, really close to 3.5. It would be a surprise after 1,000,000 rolls to get 3.9 or something for your answer. After 1,000,000 rolls, your answer should be really, really, really close to 3.5. So what we find is that the average stays the same, but the standard deviation decreases. All right, now this is actually the really important part. This is the really important part for us as we think about going forward, because what we would like is we would like to actually know the average. Well, but that means that if we do an experiment over and over and over and over again, the result of the experiment should be the average, and the result of the experiment should have a really small standard deviation. So that's why if someone wanted to say, what's the average height of a college student? If you ask one college student and say, hey, how tall are you? Well, you might have got one of the basketball players, and you might come up with like 6'8" or something. That's not a very good picture of the average size of a college student, right? So if you just ask one person, you could end up with any wide range of results. And even if you ask 2 or 3 people and take their average, it's still a little bit questionable. However, if you find the average of, say, 1,000 people, 10,000 people, then all of a sudden that average should be a really good picture of what an actual average of a college student looks like, because the standard deviation for that sampling distribution has shrunk. And so this is the real idea of statistics going forward. We want to take large samples, because large samples make that standard deviation of the possible outcomes to get smaller and smaller and smaller. Okay, so that's what I wanted to say about sampling distributions. We have some homework for sampling distributions. So here it is on our notes. I'm going to tell you something that you're going to like about that homework. We're going to skip it. So skip section 5.1 homework. That homework is interesting, and if you want to do it for your own benefit, that's perfectly fine. But as far as I'm concerned, these problems are not the most essential going forward, and due to time constraints, I'm going to try to focus us on the things that are the most important going forward. Okay, so you're free to skip these 5.1 homework assignments. Now, the next thing I want to do, though, is I want to ask ourselves, what happens as the size of the sample gets larger? Well, not only does the average stay the same and the standard deviation decrease, but we actually get something really interesting happening to the picture. If you look closely, this picture started flat, and what did it start to look like now? Now it was flat, and then it gets big, and then it gets flat again. If you're paying attention, this is starting to look like that normal distribution that we talked about so much. And what we find is that as the size of the sample gets larger, we start to get a normal distribution. What do I mean by normal distribution? Well, we talked about this in class before the break, but wow, doesn't that feel like a long time ago? I mean, it feels like a different age when we were sitting in the classroom talking about math, not sheltering in place at home. But at any rate, a normal distribution is that bell curve. It's that shape that looks kind of like this. It has this bell curve shape. And so any sample that you get, as it gets larger and larger, you get that begins to look like a normal distribution. And not only that, as it gets larger and larger, the standard deviation of the bell curve gets smaller, so our bell curve starts to get narrower and narrower and narrower. And so that means our most likely values get zeroed down to just a single point. This is probably the most important idea in all statistics, and in some ways one of the most important ideas in all of mathematics, that if you take any single sample, no matter how crazy it is, you could have you could take your dice and you could put any numbers on your dice, add any probabilities you want to each side of your dice, and if you roll it enough times and take the average, those averages will have a bell curve shape. This is the big theorem in statistics, and this theorem is called the central limit theorem. And so you can see in our notes, I've written the central limit theorem out on 5.3. I, of course, won't require you to quote it, but this is one of the really big idea in statistics. And it's that every sample, no matter how you take it, becomes a normal sample. But the central limit theorem goes even further, and that is it tells us what the average is. So this is the average of our sampling distribution, and this is the standard deviation of our sampling distribution. And we're going to write that as average with a little x bar, and we're going to write that as the standard deviation with a little x bar. And so this is the average of the sample. That's what this number is, versus over here, this is the average of one outcome. So the difference is, if you just were to, it's like if you roll your dice once, you would get an average of 3.5. If you roll your dice many, many times, you still get an average of 3.5. And so that's the difference between this side and this side. And so what this says is that the average stays the same no matter how many times you roll it. This is the standard deviation. I'll just use SD for the sample. So if you take the standard deviation for the sample, we can compare this to the standard deviation for one outcome. Now what this says is that if you take the standard deviation for the sample, you have your standard deviation for one outcome, but you divide it by the square root of n. And so that means that if you had, say, 100 samples, so we rolled our dice 100 times, we would take our standard deviation and divide it by the square root of 100, or by 10. So our standard deviation would be 1/10 what our standard deviation originally was. So our possible outcomes, the average stayed the same, but our possible outcomes became much, much smaller, much more well-known, much more precise. And if this were, say, 10,000, then all of a sudden we'd be dividing it by 100. And if it were 1,000,000, we'd be dividing it by 1,000. And so each time, as this number gets bigger and bigger and bigger, our standard deviation for our sample becomes smaller and smaller and smaller. So we're really making the difference between one outcome and many outcomes. And so these are the many outcome formulas. Okay, let's tackle this section 5.5 problem. So you might want to have your notes out and look at it. A group of epidemiologists is wondering whether there are external factors reducing the life expectancy of individuals in their city. The answer is coronavirus. Oh, no, sorry. That's too soon. I shouldn't joke about coronavirus, should I? Okay, sorry about that. They know that nationally the life expectancy is 70 years old with a standard deviation of 16.5. The researchers collect records from 50 people who died in their city. What's the probability that an individual has an average lifespan lower than 67? If we have 500 people, what's the probability that they have an average lifespan less than 67? Let's actually do a problem that goes before part A. Okay, let's do. Oh, sorry, that's the wrong one. Let's do 5.5, and let me actually do a problem. We'll go a pre part A. Pre-part A problem. The pre-part A problem is going to be you pick one person. What is the probability that they live less than or equal to 67 years? So we're just going to pick one person, and we're going to say, what's the probability that that person lives less than or equal to 67 years? Well, we're going to have to make a big assumption. The big assumption is that these people in our collection that we know of that were given in this problem have a normal distribution. But let's make that big assumption. So our big assumption, we will assume a normal distribution with mean equal to 70 and standard deviation equal to 16.5. So we've got a mean of 70, standard deviation of 16.5. And now that means that I'm looking for this normal distribution right here. And I'm just asking myself, okay, 70 is here at the middle. So I'm asking myself, if we're on 67 right here, what's the probability that someone ends up on this side of 67? Now, if you remember in class, we had lots of different ways to tackle this problem. We had lots of different ways to answer this before the notes, before we started. One option was some of you could use Excel, And if we used Excel, you would do the norm.dist command. Some of you will use your calculator. If you use your calculator, you would do the normal CDF command, and that was in your distributions menu in your calculator, or you could use your phone. I think for these demonstrations, I'm going to always use the phone app because I just think that it's going to be nice and visual for us, and I don't know if all of you have access to Excel or Calc, but I'm pretty sure all you have phones because you're like in you're young adults, and I think every young adult has a phone. So I'm going to use the phone app. So what phone app am I going to use? Well, I'm going to put on my iPad, so hopefully you can see it a little better. I'm going to use this app, this red one right here, that says Probability Distributions. And you can go get this from the App Store. I believe it's available on both. And there are lots of other probability distribution apps if you want to choose a different one. But let's go to probability distribution. If you feel really confident with Excel, really confident with the calculator, go for it. If you don't, why don't you go get that app from your phone and we'll all follow along with the same thing. So I'm going to get my probability distributions app, and then I'm going to scroll and I'm going to look for the normal distribution. And so we get normal, and you can see our picture here. So you can see that I've got my mu, my sigma, my x, and my probability. So what am I looking for? My problem, you can see I have a mean of 70, a standard deviation of 6.5, so that means I come over here. I'm going to type 70 in this spot, and I'm going to type 16.5 in this spot. And what you see is that now I've got my mean and my standard deviation entered just like I want. And now I want to find less than 67. So I'm going to put 67 in this X bar place. And then this probability over here is going to show up with, it messed up. So let's hit 67 over here and hit enter and see what we get. And what you can see is it drew the picture. Notice it drew the exact same picture I had. It had the normal curve, it has right where 67 is, and has all the values to the left shaded. So one thing I like about the app is if you're good at drawing these pictures, you can kind of know if you made the right results or not. And so right here is the value we put in. Over here is our probability. So we see that 42.7 was the answer we got. 42.7. Or 0.427 was the result. Okay, so that's if you picked one person. But the question that we want to ask, which is the question on part A, is not what if you pick one person. The question for part A asks, so let me erase this. The question for part A says, well, what if you had 50 people? What if you had 50 people? What is the probability that those 50 people have an average lifespan lower than 67? Well, how do we do this? Well, what we need to do is we need to get our new mean and our new standard deviation and solve this problem. Well, the key is going back to that central limit theorem that we had just a minute ago. So what we find is that if we have a sample of size 50, what happens to the mean? The mean stays the same. So if you have 50 people, mu of x bar is still 70 because it stays the same. However, what happens to our standard deviation? Our standard deviation doesn't stay the same anymore. Our standard deviation is now divided by the square root of n. So our standard deviation is no longer 16.5. Our standard deviation has become smaller. So our standard deviation is 16.5 divided by the square root of 50. And so now I'm gonna type that in my calculator, and we'll go 16.5 divided by the square root of 50, and we get 2.33 is what that new standard deviation is. 2.33. And so this is my new standard deviation, and this has become smaller from the central limit theorem. So what we're doing is we're using the central limit theorem to find our standard deviation for 50 people instead of just one person. Okay, so now we come back and we're going to calculate that probability. So what does our problem look like? Our problem looks like the exact same problem we had a second ago. We still have that normal distribution. We're still looking for 67. We're still looking for the area underneath. But now, instead of using 70 and 16.5, now we're using 70 and 2.33. So this number, so as I get my app, this standard deviation has become smaller. This standard deviation has become 2.33 from earlier. And so now let's come here, type 67 and hit enter and see what we get for our result. And now you can see what's happened. Our numbers have spread out, which is a way of showing our normal distribution has become skinnier. And now what's our number? Now our number is 0.09. So our number earlier was 0.42. Uh-oh, I forgot what it was. It's either 3 or 7. I'm going to write 3, but it might have been 7. Now we got 0.099. So almost 10%. So if you were to just go pick a person off the street, say what's the probability that they live less than 67 years, you'd have about a 42% chance of that being true. If you pick 10 people or 50 people off the street, average how long they live. And is that average smaller than 67? Now there's only a 10% chance. Why is that? Well, because most people are living around 67 years. So you'd expect more of them to live more than 67 and fewer of them to live less than 67. And so 67 would be, most people living around 70 years. Sorry for that. Again, I would love to edit this out and change it, but we're stuck with this. So most people live about 70 years, so to get a number lower than 67 becomes a little less likely. Well, let's try part B. So let's look at part B. This would be a good place for you to pause. So part B, we're going to switch from 50 people to 500 people. And this would be a good place for you to pause. So why don't you pause real quick and see if you can get the same results that we're going to get just a second. So ask, what is this number? What is this number? And then can you calculate out this probability from it? So pause. Okay, now that you paused it and came back, let's do this together. So hopefully you said, what's the average? The average is still 70. So with a bunch of people, that number stays the same. But down here, what happened to our standard deviation? Our standard deviation is now 500 is what we're taking. So now we're taking 16.5 divided by the square root of 500 instead of 50. And when I put that number in my calculator, I get 0.737. Maybe I'll do 8. I'll round it. 0.7379. So 0.738 is what I got for my number. And so if I come here, I'm going to be doing the exact same thing on my app. So I'm going to have 0.738 for my calculator. So let's come here. Uh-oh, I didn't want to ask for help. There we go. So now I'm going to come, I've got 70. I'm going to put 0.738 into my app. Again, if you're working on Excel or you're working on your calculator, good, those work just fine as well. I'm just using the app because I think it's going to put us all on the same page. And then I'll put 67 and hit enter. And what do I get this time? Look how small our number is now. 0.000024. Well, this is an interesting result, and this tells you the power of statistics and the power of taking a big sample. So if you are one of these epidemiologists and you're asking, I wonder whether people in our city live less than people in the outside world and people outside of our city. If you just looked at one person and their life expectancy was less than 67, then people would say, okay, what's the chance of that one person showing up and having, living to be less than 67? Well, the answer is 42%. So you'd be like, okay, that's normal. It's about, 40% of people are going to live less than 67. So no big deal. You collect 50 people in your study, and then they have an average lifespan less than 67. Someone says, well, is that weird? Is that something unexpected? Well, that would happen 10% of the time just by chance. And so if that showed up, and you'd say, okay, if you gathered those 50 people, found out how long they lived, got a number less than 67, people would say, wow, was that an unusual number? And you'd be like, oh, it's a little unusual, but about 10% of the time it would happen anyway. So maybe it's not unusual enough for us to say that this that this is really, there should be red lights around it, and this could have happened by chance. 10% probability things happen all the time, right? But now if you gathered 500 people and did the probability, now what are we at? Now we're at 0.000024. If you move it 2 decimal places, that's 0.0024%. This basically never happens. So if you gather 500 people and you find that their average lifespan is less than 67, and someone says, well, is this unusual? You can say, this is extremely unusual, because the chances of this happening by chance alone are almost zero. So the likelihood is that this didn't occur by chance. The likelihood is that there's something going on in this population that made it occur like this. All right, so let's end there. Do your 5.2 homeworks, or do your 5.3 homework sections. These problems I think will be good for you to try out. Again, you can skip 5.1 homework. This section are not the most important problems we do from the semester, but the way we think about it is critical. So thinking about moving from one moving from one outcome to a sample of a lot of outcomes is a huge difference, and will make a big difference for us throughout the rest of the semester. So thank you all, and I'll see you in office hours.